Hello, everyone, and Professor. My name is David An, and today I'm going to present about the term project. And the topic is tangent plane and differential. And it's contained 5 points like tangent plane and normal line, estimating change in a specific direction, how to linearize a function of two variables, differential, and the last one is function of more than two variables. In this subchapter, we derive the tangent plane at a point on smooth surface in space. Then we show how to calculate an equation of the tangent plane from the partial derivative of the function defining the surface. This idea is similar to the definition of the tangent line at a point on curve in the coordinate plane for single variable function, like in section 3.1. And then we study the total differential and linearization or function of several variables. Now let's look at the tangent plane and normal lines. The tangent plane at a point p sub 0 that have three coordinates like x sub 0, y sub 0, and z sub 0 on the level surface f of x, y, and z equal to c of a differentiable function f is the plane through p sub 0 normal to the gradient at p0 of f. The normal line of the surface at p sub 0 is the line through p sub 0 parallel to gradient of f at p sub 0. Now, we derive the formula of the tangent plane and normal plane. Like we see in the screen, like tangent plane to the surface f of x, y, and z equal to c at p sub 0. This is equal to fx at p sub 0 multiplied by x minus x sub 0 plus fy at p sub 0 multiplied by y minus y sub 0 plus fz at p sub 0 minus z, multiplied by z minus z sub 0 equal to 0. And the normal line to f, x, y, and z equal to c at p sub 0 is x equal to x sub 0 plus fx at p sub 0 multiplied by t, y equal to y sub 0 plus fy at p sub 0 multiplied by t, and the last one is z equal to z sub 0 plus fz at p sub 0 multiplied by t. And then we move to the example 1. Find the tangent plane and normal line of the surface, like we see in the figure 14.33, the tangent plane and normal plane to the surface at p sub 0. And now to find the tangent plane and normal line of the surface given f x y z equal to x squared plus y squared plus z minus 9 equal to 0 at the point p sub 0, we then find the gradient of f at p sub 0 by derivative f of x, y, and z respect to x, y, and respect to z. And we substitute the coordinate of p sub 0 and we got 2i plus 4j plus k. And by applying the formula like I presented above, so we got the tangent plane is 2 multiplied by x minus 1 plus 4 multiplied by y minus 2 plus z minus 4 equal to 0. Or we can simplify it as 2x plus 4y plus z equal to 14. And the line normal to the surface at p sub 0 is x equal to 1 plus 2t, y is equal to 2 plus 4t, and z equal to 4 plus t. Now, we move to the next point. Like we see the plane tangent to a surface z equal to f xy at x sub 0, y sub 0, and f of x sub 0 and y sub 0. The tangent plane to the surface z equal to f of x and y of a differentiable function f at the point p sub 0 equal to x sub 0, y sub 0, and f of x sub 0 and y sub 0 is fx at x sub 0, y sub 0 multiplied by x minus x 0 plus fy at x sub 0, y sub 0 multiplied by y minus y sub 0 minus z sub 0 equal to 0. Now, let's look at the example 2. Find the tangent plane to the surface z equal to x cosine of y minus y multiplied by e to the power x at 0, 0, and 0. First, we differentiate the surface with respect to x, and then we substitute that value with 0 and 0. So we get fx at 0 and 0 equal to 1. And we differentiate the surface with respect to y and substitute the value at 0, 0. So we got fy at 0 and 0 equal to minus 1. And then the tangent plane is 1 multiplied by x minus 0 minus 1 multiplied by y minus 0 minus z minus 0 equal to 0. And as a result, we got x minus y minus z equal to 0 is the equation of the tangent plane. Example 3. The surface is given have the equation that f of x, y, and z equal to x squared plus y squared plus minus 2 equal to 0. And another function, g of x, y, and z equal to x plus z minus 4 equal to 0. And these two curves intersect like we see in the figure. So we want to find parametric equation for the line tangent to E at the point P sub 0 equal to 1, 1, and 3. So first we find the gradient of f at P sub 0 by differentiating respect to each variable. So we got 2xi plus 2yj at 1, 1, 3. So we got 2i plus 2j. And then we find the gradient of g at 1, 1, 3. That is equal to I plus k at 0.113 and is equal to I plus k. And then we want to find the cross product of these two gradients, and we got vector v equal to 2i minus 2j minus 2k. The tangent line is x equal to 1 plus 2t, y equal to 1 minus 2t, and the last one is z equal to 3 minus 2t. Now we move on to the next point, that is about estimating change in a specific direction. So to estimate the change in the value of a differentiable function f when we move a small distance df from a point p0 in a particular direction vector u. So we can use the formula df equal to the gradient of s at p sub 0 scalar by vector u and multiplied by ds. Now let's estimate how much the value of the function f, x, y, and z equal to y multiplied by sine of x plus 2yz will change if the point P that is move 0.1 unit from P sub 0 straight toward P1. So first, we need to find the directional vector that equal to vector P0, P1 over the length of this vector. So we got 2 over 3i plus 1 over 3j minus 2 over 3k. The gradient of f at P sub 0 is I plus 2k. And therefore, we can find the gradient multiply scalar by vector u that is equal to 2 over 3 minus 4 over 3 that is equal minus 2 over 3. So the change df in f that results from moving ds 0.1 unit away from P0 in the direction of u is approximately minus 0.067 unit. Now, let's find the way to linearize a function of two variables. Like we has learned, function of two variables can be complicated, and we sometimes need to approximate them with simpler one that gives the accuracy required for specific application without being so difficult to work with. We do this in a way that is similar to the way we find linear replacement for function of a single variable, like we have learned in section 3.9. So the linearization of a function of two variables at point x sub 0, y sub 0, where f is differentiable is the function L of x and y equal to f at x sub 0, y sub 0 plus f of x at x sub 0, y sub 0 multiplied by x minus x0 plus fy at x0, y0 multiplied by y minus y sub 0. So the approximation at this point is f xy is L of xy. That is the standard linear approximation of f at x sub 0 and y sub 0. Example 5. Find the linearization of the function given that is equal to x squared minus xy plus 1 over 2x squared plus 3 at the point 3 and 2. So first we find the value at 3 and 2 by substitution the coordinate to the surface function. So we got 8. And then we differentiate the function above respect to x, and then we substitute the value 3 and 2 into that derivative. So we got 4. And then we do the same like fx, we differentiate fx y respect to the variable y and substitute them. So we got minus 1. So by substitute those values into the formula that I have present above, so we got the linearization of f at 3 and 2 is L xy equal to 2x minus y minus 2. Differential. The differential dx and dy are independent variables, so they can be assigned any value. Often we take dx equal to delta x equal to x minus x sub 0 and dy equal to delta y and equal to y minus y sub 0. We then have the following definition of the differential or total differential of f. Now we look at the definition. It states that if we move from x sub 0, y sub 0 to a point x0 plus dx, y0 plus dy nearby the resulting chain. So we got df equal to fx at x sub 0, y sub 0 multiplied by dx plus fy x sub 0, y sub 0 multiplied by dy. In the linearization of f is called the total differential of f. The last part is function of more than two variables. Like we see in the screen, 1. The linearization of the three variable function at point p sub 0 is x, y, and z is equal to f at p sub 0 plus fx at p sub 0 multiplied by x minus x sub 0 plus fy at p sub 0 minus y sub 0 to fz plus p sub 0 multiplied by z minus z sub 0. And suppose that R is a clone rectangle solid centered at P0 and lying in an open region on which the second partial derivative of f are continuous. Suppose also that fxx, fxy, fxz, fxy, fxz, and fyz are all less than or equal to m throughout the region R. Then the area E equal to f of x, y, and z minus by L x, y, and z in the approximation of f by L is bounded throughout R by the inequality. So we got the absolute value of A is less than or equal to 2 over m multiplied by absolute value of x minus x sub 0 plus absolute value of y plus minus y sub 0 and plus z minus z sub 0 squared. 3. If the second partial derivative of f are continuous and if x, y, and z change from x sub 0, y sub 0, and z sub 0 by small amount, dx, dy, and dz, so the total differential df is equal to fx at p sub 0 multiplied by dx and fy at p sub 0 multiplied by dy plus fz at p sub 0 multiplied by dz. Give a good approximation of the result chain in f. That's all for my presentation today. So good luck everyone and stay safe. Thanks for your attention.